Great. Thank you. Thank you very much for that introduction, Torsten. Thank you very much for inviting me. Um, I'm delighted to be able to connect with you from the Waterberg via the wonders of modern technology. And indeed, it is the wonders of modern technology really that I want to talk about. And central to all modern technology, as we'll see, is in actual fact an area of science called quantum mechanics. And that's what I want to think about today. So let me just start screen sharing, and I'm going to share with you a little presentation. There we go. Okay, so what I want to start off by doing is, hopefully you can all see this, just putting up the word quantum mechanics. Some of you might think of quantum physics or something like that. It's all the same thing. And I want you to think about that and what image comes into your mind when you think of quantum mechanics. Now, it might be something like this. Lots of really obscure mathematics that kind of terrifies the poor innocent civilian. But there is mathematics in quantum mechanics, and physicists do get very excited about it. And they get particularly excited about one equation, which is named after the person who invented it, the Schrodinger Equation. And they get so excited about this particular equation that they actually tattoo it on various parts of their anatomy. And that says something about the importance of the equation and the weirdness of physicists as well. So that's one thing, but I should just assure you that that's the last time we will actually encounter Schrodinger's equation. We will meet the gentleman a bit later, but we will leave the equation behind. Some of you, if I mention quantum mechanics, a picture of poor innocent kitty cats being persecuted might spring to mind. For some of you that might mean nothing, but don't worry, we will actually unfortunately have to come back to small innocent kitty cats being persecuted a bit later on. But perhaps for many people, what doesn't spring to mind is your modern electronic life. But it should, because basically every aspect of electronics relies on design using quantum mechanics, and it works using the principles of quantum mechanics. So your iPhone, your Samsung, your TV, modern TV, your laptop, the internet connection we're connecting over, all has been designed based on the principles of quantum mechanics. So you could actually say quantum mechanics is attested and tested and verified billions of times every day, if not trillions of times, by the way we now run our modern life. So it's a very important aspect of modern life, actually, quantum mechanics. And so what I want to look at today is, what are the theological implications of quantum mechanics? Now, you might say, gosh, none at all. But I just want to investigate and dig into that a little bit. And to start off, I would like to start by looking at an atom. Now, I should say at the start, this is an absolutely appalling picture of an atom, but it looked quite pretty, so I put it up anyway. It's appalling because it's totally out of scale and various other defects. But one thing it helpfully gets right is you can see that atoms have a nucleus at the center and electrons going around. And that nucleus at the center can sometimes be unstable. And if it is unstable, that can result in radioactivity. And when the nucleus is unstable, what actually can happen is something like this. Here you've got a uranium nucleus, and you've got it decaying into a thorium nucleus. So what happens is it spits out this little helium nucleus, which we call an alpha particle, and changes into a different element. And this alpha particle spins out at great speed, and so can be quite dangerous if you get impacted by it, particularly if it's inside you. So that is radioactive decay. Now, this gentleman, Hans Geiger, very helpfully invented his little Geiger counter, which enables us to measure these things like alpha particles being spat out of a uranium nucleus. So we can actually study radioactive decay and measure when it occurs. So I want to imagine setting up an experiment where you've got some radioactive material, you've got a Geiger counter, and you can set the experiment up so it's going to run for a certain period of time, And there's a chance within that, there's a 50% chance within that period that one of these radioactive decays will occur, an alpha particle will be spat out, and your Geiger counter will measure that. Now, it's very important to note that quantum mechanics tells us this process is entirely probabilistic from our perspective. So you can't say, here's my radioactive isotope, it will spit out an alpha particle 2 minutes after I run this experiment. You can't do that. What you can say is, we're going to run this experiment for 10 minutes, and in that 10 minutes, there's a 50% chance it spits out an alpha particle and gets measured, and 50% chance it doesn't. Okay, so 10 minutes, you go away, have a cup of tea, wait your 10 minutes, and come back. And what will you find? Well, you'll find, of course, that either your uranium nucleus has not decayed, no alpha particles been spat out, or it has, and it's changed into a thorium nucleus. Okay, all very simple. Here's the question. What was happening to the system while you were having your cup of tea? So you probably say, well, Phil, of course, while I was having my cup of tea, at some point, either the radioactive decay occurred or it didn't. You know, that's pretty damn obvious, really, except it's not. This is where quantum mechanics kicks in. And what it tells us is that that is not the right way to look at reality. What it says is, during that process, before we came back, while we were having our tea, in actual fact, the system was in what they call a quantum mechanical superposition. Now, don't be frightened by the terms there. To understand it completely, you do have to look at the mathematics. But basically what it means is the decay had not either happened or not happened. The system was in this funny mixture of having both happened and not happened. And it's not just a lack of our knowledge about the system. It's not that it either had decayed or not decayed. We just don't know about it until we come back and look. It genuinely had not done either. It was in a superposition of both. Now, hang on to that thought. If you think this is weird, don't worry, just keep going with me here. So the idea is, until you came and looked, it was not an either this or that. It was not either undecayed or decayed. It was the process of observation actually changed the system and forced it to decay, the wave function to collapse, some people might say under the Copenhagen interpretation, into one or other of those results. Now, at this stage, you're allowed to release your disbelief at that and say, gosh, this is nuts. That doesn't sound like reality at all. But just remember, if you really think that, throw away your smartphone. You know, don't use a smartphone, because it's totally based on this quantum weirdness. Without quantum mechanics, there's no way you could design the silicon processing units and memory storage and everything that your smartphone relies upon. So we really, really, really do know that at a microscopic level, this is true. This is what is happening. This is the only way we can understand the universe around us. Schrodinger's equation works. Okay, something else you might say is, yeah, Phil, okay, this goes on with atoms and nuclei, but this doesn't happen in real life. This is not what I see when I look around me. When I look at Torsten, I don't see a superposition of Torsten having a cup of tea and deciding not to have a cup of tea, and somehow he's a smudge of the two of them put together. That's not what we see. This is not reality. And this is a valid question. And it brings us really to the core of the issue I'm wanting to discuss this morning. And I'd like to talk about it in these terms. We know that quantum mechanics applies at the very small level. So right down here at the bottom left of the screen, I've got a collection of elementary particles, the sort of 17 particles of the standard model that we think everything is made up of in our universe that we can see, all the physical components. And of course, they make up atoms. And you put some atoms together, you can get molecules. You put some molecules together, you can get macromolecules, really big molecules important for life. You put some of those together, you can get organelles, the bits that make up your cells. You put some of those together, you get cells. And you put some of those together and you get organs. And you put a lot of those together and you get a person. Now, physicalism would say there's just a continuum there. You as a human being are just and nothing more than the sum of your parts in terms of atoms and molecules. You're just atoms and molecules. And here we really get to grips with the core of the question. We know quantum mechanics applies down here, the bottom left, at our atoms. Does it apply in the same way up here at the right, top right-hand corner when we deal with people? Now, to look at this, I'm afraid we're going to have to come back to putting nice little kitty cats in mortal danger. So some of you are very familiar with this idea. This is a thought experiment that goes back to a long time ago, very famous physicist called Schrodinger, who indeed the equation is named after. He imagined this thought experiment to try and grapple with this problem of what are the limits of quantum mechanics. And what he did was this. So he imagines taking a box, putting a poor innocent cat inside, and before, just at the start of our presentation, I should just produce exhibit A. Here is my cat. So just to demonstrate that I love cats, and I'm not actually going to do anything nasty to them. Here's Charlie. But in this thought experiment, there you go. Charlie, say hello to the audience. Yeah, there we go. They can jump off again now. In this thought experiment, a very nice cat is put inside a box. And you also have over here on the right a radioactive isotope and a little Geiger counter. And the way it works is it's let run for a while, this experiment. And during this experiment, there's a 50% chance that the radioactive element decays, triggers the Geiger counter, and that is set up so this block drops on top of this phial of poison. The poison goes into the box and kills the cat. Okay. And you run this experiment. And what happens? Well, quantum mechanics, remember, when you're waiting for the experiment to run, what quantum mechanics tells you is that radioactive isotope is in a superposition of decayed and not decayed. So that means the whole experiment inside the box, if you're a physicalist, is in a superposition as well. So in actual fact, what you've got is you've got a superposition of, slightly change the dynamic here, a superposition of decay, not decay, a superposition of the hammer fell onto the phial of poison and it didn't, and a superposition of the cat is dead and alive. Now, Mr. Schrodinger, who we mentioned, he thought about this and he said, well, wait a sec, let's imagine what happens. We've got this happening in a box and we've got a scientist outside of our box. So do we really imagine that until the scientist comes along and observes the kitty cat, it really is in a superposition of alive and dead? And if that's true, what's so special about the human being as an observer? Why is it the process of him looking at it that would cause this quantum mechanical wave function collapse? And this was sort of puzzling and is waved around quite rightly as a sort of weird aspect of quantum mechanics. But physicists are okay with weird. We're usually quite weird people ourselves. And weird is okay. But things got a little bit weirder with this gentleman called Eugene Wigner. And he thought about this and he said, wait a second. Let's imagine two boxes and two scientists involved in watching this experiment. So you've got one scientist observing this cat, and when he looks in the box, this superposition has to collapse and you get a definite outcome of a dead or alive cat. So that's his perspective. When he looks in the box, you've either got happy scientist, alive cat, or unhappy scientist, dead cat. But what about the perspective of the scientist outside the box that contains that whole experiment? He says, no. I haven't looked in my box yet. You're still in a superposition. You may think you know the result, but you don't actually, because the result actually hasn't yet occurred. I'm just about to look inside my box, and what I'm going to see is either a happy scientist, alive cat, unhappy scientist, dead cat. But right now, you, my friend, are in a superposition of happy and unhappy. Now, this gets pretty weird, doesn't it? Can conscious beings be in a superposition of states? And what about if you put another box around this whole thing and have another person observing the two scientists inside their boxes? And in fact, of course, you could create an infinite regress of boxes and scientists. So this seemed to be getting even more weird. But again, physicists can handle weird. And then things got even weirder. So at the center of this is really the question, is a person just a collection of atoms? Does quantum mechanics apply to that scientist looking inside that box in the same way as it applies to the radioactive isotope that decays? Can we extend quantum mechanics up to work on people in the same way as it works on atoms? And at this point, we can bring in this gentleman, Renato Rene, and he's added some really interesting thoughts to this debate. And this is kind of hot off the press. He submitted a paper on this in 2016. It was reviewed by Nature, where it was eventually published, extensively reviewed for 2 years, because the implications of his paper were so shocking that it really disturbed a lot of physicists. And so they really, really, really wanted to review it and check it was right. And they brought in more and more reviewers who chewed it all over. And after 2 years, they said, yep, this is right, published. So it was published in the most prestigious science journal in the world. And I'm not going to talk you through the details of the thought experiment, because unfortunately they are too physicsy. But I'll just give you the outline and the conclusions that René and his co-workers reached. So this is what his thought experiment looks like. You can see cats, and for cat lovers, you'll be delighted to know the cats are all out of danger. There's no cats involved. Instead, we've got 4 scientists, 2 of them inside boxes, and 2 of them observing the scientists inside boxes. And if you want to read about this experiment, just Google on René and Frauchiger, Nature 2018. You can bring up the original article, you can download it and try and read it, but I do warn you, it is quite messy and complicated. And what these scientists do is they do random quantum mechanical things, and they pass quantum mechanical states between each other, and they reason using quantum mechanics. And what they come up with is a logical contradiction. Now, physicists are happy with weirdness. Logical contradictions, not so much. That's worrying. You know, that's a red flashing light. Physicists call this a no-go theorem, and it gets them worried. And so Mr. Renner and his co-worker Frauchiger, they said, well, something's wrong. Something is wrong here. Let's go back and re-examine the original assumptions that went into our thought experiment. And so they discovered, there were basically 3 assumptions that they were making. The first assumption was, if you measure something and then I measure the same thing, we have to get the same answer to our measurement. Now, this does seem fairly blindingly obvious, doesn't it? And indeed, what you're looking at here is the assumption that there is a real reality that we can all observe. So this assumption is really quite basic to the whole process of science. You throw this out, it's not clear what science you can do, or indeed what kind of world you have. If I can measure an alive cat and you can measure a dead cat, or I can measure an electron to have a spin up and you can measure it to have a spin down, and it's the same electron, it's the same cat, that kind of doesn't make sense. We've got a very weird understanding of reality if that's the case. So no one really likes that one. The second assumption was, if I use quantum mechanically correctly, and so do you, then I can think about how you must think about quantum mechanics, and we can get the same answer to the same question if we do our quantum mechanics correctly. So this also seems pretty basic. And if it's wrong, then maybe we must all give up quantum mechanics, but we kind of know quantum mechanics works. So this is a pretty radical assumption to throw out as well. That leaves us with our third assumption. And this assumption is basically that quantum mechanics applies to people, because they're just atoms and molecules. And we know it applies to atoms and molecules. We've done the experiments. So people are just atoms and molecules, aren't they? So it must apply to people. Now, this is couched in various terms. If you read about this article, it's quite interesting. Some of the commentators will say that it applies to systems as large as humans. That's not actually the assumption in the thought experiment. The assumption is not about the size of the system, actually. The assumption is it applies to humans. That's the assumption. Humans, conscious reasoning humans, can be governed by quantum mechanics. That is the assumption. Okay, so which of those do you want to throw out? All of them have quite radical implications. And physicists are very have been quite shaken up by this. You'll find the literature is full of articles written sort of ranting about this, trying to offer explanations, scratching of heads. Leifer from Chapman University offered this rather interesting perspective after looking at this paper. He said, it's likely we're making some implicit assumption about the world, the way the world has to be, that just isn't true. Once we change that, once we modify that assumption, everything would suddenly fall into place. Now, I would agree with him, and I would say it's the assumption of physicalism. The assumption indeed that we know we're atoms and molecules, but are we just atoms and molecules? Physicalism says, yeah, there's nothing more, nothing else to look at, move along. I think the Bible is very clear and theology is very clear that we are more than atoms and molecules. And I think that is the implicit assumption that we're making, that we need to change. I'd just like to talk about that in terms of just going back and looking at if we change those assumptions. So first off, changing the first assumption would be, if you measure something and then I do, we can get different answers. It really doesn't sound good, does it? That is, we don't have a true reality to observe. We each have our own individual realities. It's an extreme form of relativism. If I use quantum mechanics correctly and you do, we can still get different answers to the same questions. That's also pretty weird. So finally, we're left with quantum mechanics doesn't apply to people in the same way as it does to atoms. And that's the assumption that I think that's the right way of thinking about the results of this thought experiment. Okay, so I just want to look at the implications of that. Is quantum mechanics doesn't apply to people, and people are not just a collection of atoms. This takes us back to the work of a very famous scientist, and I would just like to put that up. So what I believe this thought experiment is saying is a person is not just a collection of atoms. Quantum mechanics, she say no. That doesn't seem to be the way the universe is. And this very important scientist I'd like to bring us back to in conclusion is Richard Dawkins. He's a biologist, but he's made some quite sweeping statements about the way he thinks the world is made up. And probably his most famous of all is the following. In a universe of electrons and selfish genes, blind physical forces and genetic replication, some people are going to get hurt, other people are going to get lucky, and you won't find any rhyme or reason in it, nor any justice. The universe that we observe has precisely the properties we should expect if there is, at bottom, no design, no purpose, no evil, no good, nothing but pitiless indifference. Cheerful chap, isn't he? But he's right. If his argument holds, then the bottom line really holds as well. But I just want to look at his argument in the light of the results we've just been dabbling with in quantum mechanics. So he starts off with saying, in a universe of electrons, selfish genes, and blind physical forces. So basically, he's saying, in a universe where we are nothing more than atoms and molecules, the following would result. And then he says, that's the universe that we observe. We observe the universe is just made of atoms and molecules. There's nothing more to it. And so the conclusion is no design, no purpose, no evil, no good, nothing but pitiless indifference. Is he right? Well, the really interesting thing is quantum mechanics challenges his assumption there that that is the universe we observe. Quantum mechanics really seems to say, no, actually, think again. The universe seems to be more than just atoms and molecules. There's something else going on, which is quite a relief, isn't it? Because it means we don't have to accept that conclusion at the bottom. No design, no purpose, no evil, no good, nothing but pitiless indifference. So I think it's a very brief summary, and I've skipped an awful lot of stuff to do with quantum mechanics that is relevant to this, but I just wanted to make all of us aware of this recent work and where quantum mechanics is pointing us. Of course, we don't have a theology of quantum mechanics. It's not the basis of our faith. The basis of my Christian faith is based on the fact that Jesus Christ died on the cross and rose again, and there's very, very good evidence for that. And that's why I think actually the world is not just made of atoms and molecules. I know there's more, and there's a God, and there's a spiritual world, and there's a God who loves us. But it is interesting to note that the results of quantum mechanics are also pointing in the direction away from a universe of just atoms and molecules. Thank you very much.
And around the idea of how in quantum mechanics, what we see is used to describe what is not seen type of principle. And I'm thinking about it in the context of theology, where we are constantly in this back and forth trying to prove God. Because I think sometimes in theology, we get too stuck looking for different answers that we lose sight of what the bigger picture is. And we stop, in a way, innovating and looking for better and clearer answers. It makes sense.
Yeah, I hope I understood that. I think from a personal perspective, I did an astronomy show last night, and we were looking up at the amazing glory of the universe, and this. We talked about physics, and we talked about galaxies and supernova and all these kind of things, and that was all fascinating. But for me, the core of it was the creator and sustainer of all of this majesty knows you and loves you and actually gave his life for you. So I think we're always in this tension. God wants us to enjoy all the complexity and majesty of his creation. But on the other hand, the gospel is really, really simple, and we mustn't lose sight of that in the weeds, as it were, of everything else. The very, very simple fact. I think it was some famous theologian, or was it F.F. Bruce or someone who was asked to sum up the whole of his theology. And he said, yeah, it's Jesus loves me, this I know, because the Bible tells me so. That was what he'd learned from 50 years of theology. So I think we have to, yes, look at these amazing complexities, but they're not the core of the gospel. The core of the gospel is that God loves us, and we know that because of the death and resurrection of Jesus Christ. So I think we must handle that tension of looking at the evidence for God in creation. And I mean, Paul says very clearly, we can see God at work through the splendor of creation. David talks about it, but that's not the core, because God has done much more than that. He's given us a very special revelation by coming in person to give his life for us. I don't know whether that helps, or did I catch the core of your question or miss it?
Yes, it does. Thank you.
Phil, we have some things coming in fast and furious. Let me just start with the question on the chat, which is, does the observer have to be human for this? What if the observer is a computer or animal? And I think if I can throw in a sort of a follow-on to that, what this concept of observation seems to be very, very key in quantum mechanics. What does it mean to observe?
Absolutely, and this is a huge discussion. And about this discussion, physicists break up into multiple camps, different interpretations of quantum mechanics. Now, I've only been able to really offer an interpretation in terms of what they call the Copenhagen interpretation, which involves the collapse of the wave function. And at the core of that is this huge question, who goes around collapsing wave functions? And John von Neumann, who many people think is the cleverest person that anybody knows of who's ever lived, he was this amazing Hungarian Jew who did his physics at the start of the 20th century and just produced the most unbelievable results. And he got to work on quantum mechanics, and in 1932, he wrote a very famous book that everyone refers to in quantum mechanics. And he said, yeah, what's going on here is this collapsing of the wave function has to be driven by something non-physical. Otherwise, it's just part of the physical world. So how does the physical world go collapsing itself, kind of thing, if you see what I mean? He said, no, there must be something else. And he said it's the consciousness of the observer that must be involved in the collapse. Not such a popular view amongst physicalists nowadays. And of course, it raises the question, who's conscious enough to collapse wave functions? And that was kind of the subject of my earlier talk, at TGIF maybe a year or so ago. So it's the easiest way of addressing that is it's a very hot topic in the foundations of physics. If you believe in the Copenhagen interpretation, who gets to collapse a wave function? It's not obvious what the answer is. I believe it is to do with consciousness, and I believe that is actually the exclusive realm of humans, because I believe of God's created order, we are the ones he imbued with a soul and a spirit in order to relate to him, and that makes us special and different from the rest of creation. And I think that's why we play a special role as observers. And basically, John von Neumann also thought the same, and so did Eugene Wigner, and quite a few prominent physicists have come to that conclusion over the years, that consciousness is the key component that does the collapsing.
And then just link that explicitly back to Nat. So can an animal or a computer do the observation?
I would say no, because I don't believe they're conscious. That's the subject of a whole other discussion, the one I gave before. But subjective experience that we call consciousness, as far as we know, is unique to humans. It's not to do with behavior. You can't tell whether it's there from behavior. I can't even tell that you're conscious, Torsten. You might just be what they call a p-zombie, but I'm assuming you're not. But that's really, I'm putting theology on top of the science there. That's my personal theological view. The science would say, gosh, there's something weird going on, and we really don't know who gets to collapse wave functions, basically, whether it's just humans or whether your cat can as well. Science doesn't really provide an answer to that. It does seem to suggest, as my talk hopefully demonstrated, that something is going on where people in particular are doing something different to the rest, to just atoms and molecules. Whether cats and dogs and monkeys and whatever do as well, that's a different question that science at the moment can't answer.
I've been noticing over the internet and various other ways that others who are not Christians have been buying into this amazing sort of obscure side of quantum mechanics and using it to justify all kinds of snake oil. You know, it sort of opens the door to a whole field of magic. And I'm just wondering, Philip, if you've got any ideas about how we can stay on the straight and narrow while accepting that reality is much bigger than we ever thought.
That's a very good question, Claude. I think a good way to stay on the straight and narrow is to subject all our ideas to the analysis and scrutiny of the scientific community. Because, you know, if it's snake oil, they'll put their hand up and say, beep, no, that's rubbish, that's not true. And a whole lot of the stuff that one does hear about quantum mechanics is obvious rubbish to someone who knows about quantum mechanics. So I think what I like about the work of Schrodinger, Wigner, and Renate Renner recently is this is really, really mainstream science. You know, Renner's paper in 2016, as I said, went through an intense review process before it was published in Nature. And there's a fairly universal agreement amongst scientists that this thought experiment is valid, and his conclusions that you have to chuck out one of those three assumptions are also very widely accepted. And then it's just a case of discussing which assumption to chuck out and what the implications of that are. So I think this is where the scientific community really helps. And I think this is something that, you know, in general, not just when it comes to quantum mechanics, when we're dealing with, sorry, I'm going to be controversial here, but things like vaccines, climate change, it's really helpful for ideas to have been run through the scientific community and the scientific peer review process. And if someone comes up and says to you, I've just seen this wonderful thing on the internet that proves global warming is a myth, you want to ask, has that been published in a peer-reviewed journal? Has that been subjected to the scrutiny of the people who really, really know about that subject? And if the answer is no, then we need to treat it with a certain amount of skepticism. And I'd say the same about quantum mechanics. You know, there's all sorts of Eastern mysticism, the Tao of physics, you know, and quantum mechanics justifies Buddhism and all these kind of things. And most physicists are appalled at that because it really is in the snake oil category. The stuff we've been talking about this morning is not in the snake oil category. It's really gone through the peer review process and it's accepted as valid.
There's one on the chat by Ron. Could the Holy Spirit in us reflect any scientific atom makeup? I'm not sure if that is clear or not. Attempt to answer that in a way that won't appall physicists.
You know, I think the thing to realize here is, from a Christian theological perspective, it's pretty clear that the physical exists, so the atoms, and the spiritual exists, like the Holy Spirit. And in Jesus, the sort of God and the physical were fused into a human being. But they are, in one sense, distinct realms. You know, that from the biblical perspective, there is a spiritual realm and there is a physical realm, and the two interact. And they interact in us as human beings. But I think they are still, in one sense, distinct. And so, but there definitely is interaction. So I think what we do physically has a spiritual effect, and what goes on in the spiritual world has a physical effect. So I think is that maybe getting at the kind of issue you're raising there. So if I go along and, for example, I worship God, I give our Creator the praise and worship that's due his name, I'm a physical being, but I'm having a spiritual effect. I'm interacting with the spiritual world, and the blessings of the spiritual world and the results of that interaction will flow into the physical. So there's a strong linkage there. And the Jewish culture has a very strong awareness of that though distinct, they're also linked, and we are a unity in the physical and the spiritual being put together.
The question that, by the way, I'm quite comfortable with the idea of superposition.
Good.
Just because when you observe life, a whole bunch of life actually sits in that space of sort of becoming, but not quite there. You know, I mean, if you think of age, for example, I personally think that even though I'm a 42-year-old man, I'm also a 2-year-old toddler, you know, because I've collected that age, and it's in me. So I'm as much a teenager as I am a grown man, because that's been all internalized within me. So that helps. You know, for me, I can look at superposition and say, yeah, that makes sense. I've collected all these things, and right now, empirically speaking, I'm 42. But in fact, you know, I've collected all these ages before. So I don't know if you would have if I can draw out something, a comment from you around that, just to say that, you know, the natural, even word becoming flesh, for example, in the Bible, the word became flesh and dwelt amongst us. That's a superposition for me, I think. So yeah, I think it's more than there's a place where these things merge. You know, which doesn't have to discount the one or the other.
Yeah, I think the way I would look at that is in terms of analogy. So, you know, these things were becoming flesh or whatever can be analogies for superposition, but quantum physicists would say, if you want to understand superposition, really, you've got to do the maths. You've got to get into the maths of quantum mechanics. You've got to understand the Schrodinger equation is a linear equation. And so anything that is a solution to, if there are two different solutions to Schrodinger's equation, the sum of the two, some weighted sum, is also a solution. And there is a wonderful sort of light bulb moment that goes on when you mess around with the maths. And I think without the maths, there are elements of it that even by analogy, one doesn't quite grasp. and that produces a lot of the head scratching, I think, that we have when we talk about superpositions. And so that's why physicists get so excited about the maths. Do the maths, get into the Schrodinger equation, then you'll understand superposition. So yeah, I think you're right. It's levels of understanding. If you really want to get to grips with it, you do need to get into the maths of the equations involved, which requires quite a bit of work and time and effort to really understand differential equations and linear algebra and this kind of thing.
I was interested in the contradiction that was arrived at. In my experience, it looks like we get contradictions when we get to a point almost like the end of science or the end of mathematics. In other words, we're trying to do something which we can't do. So maybe the best way to say it is, it's sort of try to get the limits of understanding a system in which you yourself are. So we can observe things lower down, if you like, but we cannot make categorical statements about something beyond ourselves. So trying to understand a system from within a system in its entirety is a problem. So for example, you talked about the physical and the spiritual. That already is telling us that from the physical, you can't define everything from within. There has to be, and scientists try, but when they get to that point, they come to contradictions, or they come to answers that can all equally apply. So I'm not sure if I'm explaining myself, but if there's an element of that.
I think there is indeed an element of that. And the more humble amongst the physicists have really been grappling with that. That is a hot issue within the foundations of quantum mechanics is, gosh, exactly that. We're in the system. Can we fully describe the system? And I think that's a very helpful thought. And I think humility overall is something that is a bit lacking in some scientists. And science would actually do better with a fair dose of humility. I think the problem is you use the equations and you get amazing results and you produce extraordinary technology. And one can wrongly think, well, wow, we understand everything. We're so cool as humans. And we don't. There's a lot more going on. And the nice thing about this thought experiment is exactly as you say, when you hit a contradiction, it can help you stop and say, gosh, somewhere along the line, I've gone beyond my pay grade here. I'm too big for my boots. And maybe we just need to take a step back in humility and challenge some of the assumptions that have got us to here. And that's sort of what's going on in the scientific community to some extent. Some people are famously just wanting to ignore it. There's a very famous physicist called David Merman who, when dealing with this exact problem in his lecture to his students, he said, don't think about it, just shut up and calculate. Don't let the real issues get into your head. And yeah, I want to do the exact opposite. I want to think about the implications of these issues, because I think life is more than making a slightly better smartphone. It's actually to do with the answers to these really important questions.
Thanks. Can I maybe just follow up a little bit? You talked about Professor Dawkins and that series of logic, which is entirely correct. But what makes me laugh the most about that is that, in a sense, one part of his brain says there is no meaning and so on, but another part of his brain hates God with a passion. I mean, the emotion that he writes, with which he talks about the God of, our God that we serve, is so different from what he says about there is no meaning, there's no nothing, and yet there's this incredible cry that there should be something, but it's maybe he's hating this thing that we say it is. So that's an interesting contradiction. He's so emotional about this nothingness.
Exactly. And he's even contradictory in the language in his books. So he says, there's no good, there's no evil, and this Christianity thing is really evil.
Absolutely.
Wait a sec, is really that thing you've just said doesn't exist. So exactly so. I'd love to meet Richard and talk to him. My daughter actually has a very interesting paper she's been working on, just looking at where the incredible angst of the campaigning atheists come from. She's got some interesting conclusions there. But I think Richard is obviously a person in some level of turmoil, because he's wanting to put forward this philosophy that he can't actually live, because he knows that's not the way life is. There is good and there is bad and there is moral and there is immoral, and we can't live if we think everything is completely purposeless and meaningless. So he's wrestling with that internal contradiction. Absolutely.
There's quite a few things coming through on the chat, and I'm not sure in which order to take them, but there's one question about I suppose in a sense, the objectivity and integrity of the peer review process. So it says that the peer review process appears in recent times to have taken on pressure to conform, I presume, to particular agendas, and some examples are given. And the question around that is there any dogma regarding quantum mechanics?
I love the peer review process. It's a bit like Churchill. You know, Churchill said democracy is the worst form of government except for all the others. And you might say peer review is a bit like that, because it's really difficult to see anything better than peer review. Peer review actually does work pretty well, because what it does is when you have something that you think is a good piece of science, you put it out there for all your very well-informed enemies to take pot shots at it. That's what peer review is. So, you know, I've been here and I know about this. Some of my best papers were really attacked and tried to be taken to pieces by my competitors, purely for the reason that they were my competitors. But the great thing about peer review is that process rolls along, and errors, mistakes, dodgy stuff in your work will come out. One thing I like to say is the most important thing you need to know about scientists is that scientists love pointing out each other's mistakes. It's a way of getting kudos. So if something's been through the peer review process properly, it's very unlikely that any fundamental mistakes would have slipped through. I mean, they do occasionally, but that process is really, really good at culling out rubbish and culling out error. And it's the best one we have. So if something is not submitted through that, the question you should ask is why? Why is it not gone through peer review? So there are journals that effectively don't do peer review. I would immediately, my red flashing light would start flashing at that point. It's like, are you really doing science? What are you scared of if you're not doing peer review? But so in terms of dogma regarding quantum mechanics, individual people might have dogma. The great thing about the peer review process is everyone gets a bite. You know, and that's absolutely what's happened with this René and Fraschiger paper. If you look at the review process, these reviewers laid into this and that and the other and chewed this over and asked, what about this, what about that? And it took 2 years because it was such a complex question. But in the end, they kind of like, yeah, you've got this right. This is a good piece of science, let's publish. And that's a great process to put knowledge and scientific work through. And I think everything that we want to consider science should go through that process. And it's a great one for eliminating personal bias, snake oil, all these kind of things tend to get filtered out by the peer review process in a way nothing else can. So I'm a big fan of peer review and the way the scientific community functions. And it's very important to realize that, you know, there isn't a scientific worldview. You know, within science, you've got my daughter's at the moment studying Cambridge, a course on science and theology, being taught by really eminent scientists who are wonderful, wonderful Christians as well. And she's loving it. And her tutors are also demonstrating the love of Christ in their personal life. Sorry, a bit of a tangent there, but don't ever think that science is dominated only by atheists. There are atheists. There's the Richard Dawkins, but there's also the Dennis Alexanders and the Bob Whites and the Keith Foxes and the Francis Collins and these amazing, brilliant scientists who are passionate about Jesus as well. And they're also publishing in peer-reviewed journals and doing good science.
Is this experiment not simply an indication that we are misrepresenting the implications of quantum mechanics, or more seriously, are still missing a more fundamental piece of maths or physics that will actually resolve these types of paradoxes?
Yeah, that's a very, very good question. So that is one conclusion that people have drawn, is maybe quantum mechanics is not a fundamental theory. Maybe there's something deeper, and quantum mechanics, maybe we're exposing the flaws in quantum mechanics. And I would sort of say yes, because there's a more deeper reality. The interesting thing about quantum mechanics is it is the best attested theory in the whole of physics, both in terms of number of tests and in terms of the accuracy to which quantum mechanical results can be verified. And if you're working in the area of the extreme verification of quantum mechanics, people are used to getting verification down to 13 decimal places. Every time quantum mechanics is being tested experimentally, it comes up trumps. So what physicists would say then is a deeper, more fundamental theory will have to include quantum mechanics as a very, 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 very good approximation that works in almost every case. And the deeper theory will really explore levels to which quantum mechanics can't yet probe, if that makes sense. It will be more different in its metaphysics than in its physics in some ways. An example would be like a general relativity and Newtonian gravity. Newtonian gravity is really, really good, and so we still use it. It's what you study at university most often, because general relativity is too complex. But general relativity is the real truth, but it's so complex that we tend to use the Newtonian gravity because it's very, very, very good approximation. And it could be that something similar is going on with quantum mechanics, that there is a deeper, different way of looking at the world that will resolve these paradoxes. I think it's more likely to be a question of those three assumptions, that the maths of quantum mechanics is right. It does the stuff. It helps you design your iPhone. It's the philosophical implications behind it that, we're nothing but atoms and molecules. That doesn't come out of quantum mechanics. That is a philosophical, a worldview assumption that's put into quantum mechanics. And that's why I think the most likely resolution of this paradox is what René and Fraschiger have done, is they've gone and say, okay, where have we gone? Quantum mechanics, the maths is right, but where have we gone wrong with the assumptions that we're feeding in at the front end, as it were? And I think that assumption that we're just atoms and molecules is the most likely one to be wrong. And from obviously a biblical view, and many other areas of evidence, I'm sort of writing a book on this rather slowly, there's many other lines of evidence that really suggest humans are a lot more than atoms and molecules. In fact, the most important parts of our experience as a human are because we're more than atoms and molecules.
I think the thing I'm struggling with is, from my perspective, the discussion we've had today is more philosophical. The implications of, and you mentioned right at the beginning that quantum mechanics has a huge impact on technology today. And maybe this is too complicated a field to go into, but my question is how? I mean, it's sort of, if you're in both a state and a non-state or somewhere in between, I just don't know how that translates into the technology that we use today. I'm not sure if you can give some kind of illustration. It's probably much more complex than a layperson can understand. Thanks.
Gosh. Thanks, Natalie. That's a very interesting question. I think the easiest way to broach that is to just talk about the fact that quantum mechanics was developed out of a real sort of crisis in physics at the start of the 20th century, and it all related to this whole series of results coming in that really suggested these weird effects like superpositions and entanglement, and these results firmly established that, and out of that came the Schrodinger equation and the understanding of this thing called a wave function. And when you look at the way the semiconductor systems in your iPhone are designed, or the lasers that send your information around the internet, they're all designed absolutely based on Schrodinger's equation, which implies the wave particle duality kind of thing, the superpositions, it all flows out of that. So without that understanding, your whole design process would be wrong. And what's going on in the little semiconductor chips, all the sort of transistors and everything, you're always getting quantum mechanical superpositions. And if you don't take that into account with the way you design it, your device just won't work. So it's a bit like, trying to design an aircraft without understanding aerodynamics. It's not going to fly very well. So that's what I mean. It's absolutely foundational to the way you do any electronics nowadays. You have these wonderful, amazing programs that can simulate, using Schrodinger's equation, using these basic tools of quantum mechanics, simulate how your device is going to work. And if you don't use that, you're not going to design a device that works, basically. So if Schrodinger was wrong, nothing that we have in our electronic life would work or could be designed, basically.
I read a book last year, Life on the Edge, looking at quantum biology. It's a few years old now, 2014, I think. But the thing that struck me was that people were understanding some of the processes that go on in a whole new paradigm. And I just wondered what's happened since then, and whether we could have a paradigm shift in our understanding of biology, which would then help us revisit the way that life has come about on Earth and revisit the evolutionary paradigm as it sits at the moment. But again, I'm not a quantum physicist, but I just, as I was reading, I thought this feels like they're understanding things in a completely new way. Yeah, your thoughts?
Yeah, I mean, I'm aware of some of the work there. I mean, what's really interesting, for example, is people are able to show that some of the basic processes that drive our whole existence are really evident, well, really show clear quantum mechanical effects. But perhaps the most famous is photosynthesis. If you look at what goes on in photosynthesis, you can clearly see quantum mechanical superpositions in action. So without kind of quantum mechanics being a real thing, the grass wouldn't grow. It's that kind of basic. I'm not sure whether that's going to feed through to major implications in terms of things like the theory of evolution. I think it's going to be really helpful in doing things like, for example, designing more efficient crops. I mean, people are really literally looking at this. Okay, we can understand photosynthesis now better in terms of this quantum mechanical process. What can we tweak to increase the productivity of our sugarcane or whatever? I think that's more likely. It's more likely to be a practical thing, but who knows? Maybe the philosophical implications will become apparent as well.
Right.
Hi, Phil. So I think I was kind of the question was an extension of what Nat I think was alluding to. And maybe let me phrase it this way. Are there any other theological implications that you would like to let us in on that you've observed from quantum mechanics that derive from quantum mechanics? So is there anything else that you would venture into as a sort of direct implication or theological implication because of quantum mechanics?
I think for me, this whole issue of, is a human just a collection of atoms, or is there something else to us? I think this is the core of it in terms of theological implications. Yeah, I mean, the whole issue of consciousness comes into it as well, and there are connections there. But I would say the main implication is to challenge our physicalist worldview. That's the way. Not completely rule it out. I think that's too extreme. But one way, slightly different topic, but so I had a Christian talk about it. He's saying, if you're going to be a physicalist, you've got a bit of an intellectual burden to carry now. It's a bit more difficult to be a physicalist because of the implications of stuff like this. And that's the way I would put it. And so in some ways, it's quite a sort of mild aspect of what I'd really like to talk about. On theological issues, the real story is Jesus. You know, we're never going to have a gospel of quantum mechanics. It's not going to be like that. It's just going to provide little hints that maybe wake us up and make us look towards the creator and sustainer of the universe, who's also our savior. So I'm very aware that I don't want to create some kind of gospel of science, because there ain't one. You know, that's not valid. But the natural world can push us in the right direction, point our attention towards Jesus. So I don't know whether that helps, but basically the core takeaway from here is, for me, it's just a little someone tapping me on the shoulder and coughing quietly and saying, you know, look here, look beyond just the physical. There's something else going on. That would be sort of how I would summarize it.
So, I mean, this is a sort of thick question, but I'm sure if you ask the average guy on the street, you know, are we more than a collection of atoms? He'd look at you as if you think it's a completely stupid question, because it's blindingly obvious that we are. So, comment.
Yeah, I would agree with you. Sometimes the understanding of the man on the street can actually be better than the understanding of the specialist who's gone down a rabbit hole. But, you know, within science, the overwhelming worldview is physicalism. It is that we are just a collection of atoms and molecules. And I think it's driven by lack of humility, you know, because our physical theories have been so effective and led to things like smartphones and getting to the moon and all these amazing things. It can lead to a bit of hubris. Can we think, wow, we're so amazing, gosh, our physics has done all of this, our science has done all this, and therefore there's nothing more than the physical world that we can manipulate. And it's really interesting that at the sort of edge of science, the answer is coming back, no, you know, there's something else going on here. But the man on the street, as you say, is quite aware that we're more than atoms and molecules.